In this lecture, let us understand the other important signal that we get in electron microscopes, which is electron diffraction patterns. Now, electron diffraction is extremely important to understand the crystal structure of materials. This is what makes a transmission electron microscope all the more powerful tool, especially for crystallography, because from the same area where you are observing a microstructural feature, you can get a corresponding diffraction pattern. If I draw a comparison with X-ray or neutron diffraction, I am usually getting diffraction pattern from a bulk sample. Now, on one hand, understanding crystallography from bulk diffraction is very important to know once you've synthesized a new compound, or when you're checking bulk crystallography of any material, it is important that you get an idea of what sort of a crystal class the material belongs to from X-ray diffraction or neutron diffraction. How does electron diffraction help you? Once you start imaging in a TEM and get the conventional bright field images from specific regions, you might want to understand how the diffraction patterns are and how the arrangement of atoms inside that particular region is. So let us see what exactly a diffraction pattern looks like. I'll be recollecting or recalling a few concepts which are introduced at an earlier stage in this course. Mainly, if you remember, I was mentioning or describing that image is a spatial distribution of intensity. On the other hand, diffraction is a radial distribution of intensity. Let us see how these diffraction patterns look like, what are the similarities and differences from X-ray diffraction, and what is the origin of the signals that you get in a diffraction pattern, and how do you analyze them and index them in the next lectures. I'll first show you how the diffraction patterns are obtained, and we'll discuss a little bit on how to get them really at the TEM by showing some experimental demonstration sessions. And while we analyze the data that is obtained, we'll understand indexing of the diffraction patterns. So if I look at electron diffraction, this is an example. This is an example of common diffraction patterns you see. As you can see, there is two-dimensional distribution of intensity, and there is a sort of a very bright spot at the center. And if I look at the distances in both the directions, there is somewhat drop off of intensity as I go farther away. Now, if you recollect how an image is formed in a microscope, we introduced the concept of imaging of light through an aperture, and then this shows you a sort of a sinc function or a point spread function. Likewise, when I have a circular aperture or a small portion of the specimen interacting with the electron beam, say I have a specimen like this and I have a cylindrical cross section, a small area of my specimen which is interacting with the electron beam. The atoms that are internally arranged within this interacting portion, once they satisfy Bragg's law, they start forming these sort of diffraction patterns. We'll understand how these diffraction patterns are similar to what we see in X-ray diffraction and how are they different as well from X-ray diffraction. So a few characteristic features of diffraction patterns are the distances in the diffraction pattern correspond to the angles of scatter from the specimen. So let us say the deviation here is approximately 2 or 3 milliradians. The distances I measure here, and as you can see, when I see a two-dimensional distribution of intensity in spot patterns, I can always index these with some unit vectors, and these unit vectors, if I call them, are G1 and G2. They would have some value inversely proportional to the distance from the crystal structure that I have in the sample. So let us understand how this relationship is in the next slides. But essentially what you should understand is from the central undeviated beam, you have the brightest intensity, and as I go farther away, the intensity of these spots starts decreasing. So as you can see, the intensity decreases with the scattering angle, and it strongly varies with the specimen as well. Now, if I have a crystal system in which I have only one kind of atoms, I may not see any differences in the intensities of these spots. If you recollect the concepts of structure factor that was introduced, the amplitude of these scattered spots in diffraction patterns correspond to the angle of scattering and the atomic number as well. So, when I have differences in the atomic numbers within a unit cell as well, and if they are arranged in a periodic fashion, I would naturally start seeing some differences in these intensities as well. So, let us see how you obtain diffraction pattern in the TEM. In fact, in one of the earlier lectures, I just told you that by flick of a switch, you can actually obtain a diffraction pattern in a transmission electron microscope. So, let us look at it with help of some kind of a schematic diagram, and let us say I have a specimen placed here and my electron beam is like this. When the electron beam goes through the specimen and I collect the forward scattered electrons, they start converging first at the back focal plane of the objective lens, and if you remember, when you look at the angle of scatter for X-ray diffraction, this is one of the most common derivation we always come across. I have significant angles of scatter here, and if these are two planes of atoms separated by a distance d, I know that my path difference is this little value here, which is, so if this is d, this becomes d sine theta times 2. So, from here we know n lambda is 2d sine theta. When my lambda is of the order of 1.54 angstrom like in X-rays, this angle of theta cannot be ignored, and it usually ranges from 120 degrees, or you can always say it is from 0 to pi radian. It is a significant measurable angle. So, the construction of X-ray diffractometers is somewhat where you have a goniometer which is rotating and you have a detector which is placed at a distance, and you start recording data. Now, when I look at how this changes in the context of electron microscopes, is the lambda here is of the order of 0.038 angstroms if I have a 100 kV electron beam. So, if I use this in the Bragg's relation, my lambda is already lower by an order of, by 3 orders of magnitude, and as a result this angle theta becomes extremely small. So, when my lambda is much less than 1 angstrom, my theta, which is formerly in case of X-ray diffraction in the order of a few radians, it also drops down significantly lower or almost equivalent to 0 degrees. That means when I have an X-ray diffraction versus electron diffraction pattern, let me use a slightly different color for convenience here. So, if my electron beam is going nearly parallel to the plane of atoms, I would then have the satisfaction of the Bragg's condition as well. So, what this actually tells me is, in a crystalline sample, when an electron beam is incident and it is satisfying my Bragg's law, the angle of incidence is more or less 0 or nearly parallel to the electron beam. So, if I am orienting my specimen with the help of the specimen holder such that the internal atomic planes are having an orientation along the electron beam direction. So, this concept of orienting my specimen along the electron beam direction is called as orienting along the zone axis. These incident electron beam, if I look at it, it is like a cylindrical volume of interaction, and all the planes that are now satisfying the Bragg's law are parallel to the electron beam. And if you recollect, within an objective lens, all the parallel rays going through the specimen now converge at the back focal plane. So that means my diffraction pattern is at the back focal plane of the objective lens. So when I make the back focal plane as the object plane for the projection lenses here, I see the diffraction pattern. So that is what you see in a transmission electron microscope. So let us understand this in a little more detail. I'll draw your attention to one of the earlier discussions we had. So suppose I have an object which is placed very close to the lens, which is the case in a transmission electron microscope. Your distance is extremely small, and you can say that my object here is coinciding more or less with the field or the magnetic lens that is used in electromagnetic lens that is used in a TEM. At the back focal plane, I have already established that the intensity in the object plane is related to the intensity in the back focal plane through a Fourier transform. Now, if I use the same logic, what I then see is I can actually relate the crystallographic planes which are oriented parallel to the electron beam, as we saw in the previous slide. They all go through the lens and they all converge at the back focal plane, and as a result I start seeing the projection of all the planes that are parallel to the electron beam. And as you can see, the radial distribution of intensity for a sample like this is random, but when I have a crystalline sample, this changes. So how does it change? If I look at an example like this, if my object is a periodic material like this and the crystallographic planes are oriented in specific directions, I can actually represent these directions in real space with two real space unit vectors. In this case, because it appears like projection from a cubic sample, both the unit vectors are the same. But in reality, these are my actually measured unit cell vectors from a lattice fringe image. And if I now take a Fourier transform from this image, the Fourier transform appears like this, and I have two sets of unit vectors which reproduce this entire reciprocal space. And if I make this information, which is at the back focal plane, the object for the image plane, the object for the imaging lenses which follow beyond the objective lens. So one thing that I didn't mention is we were visualizing the electron beam propagation along the vertical direction, but for convenience in this I have made the electron beam propagation horizontal, and this is how my diffraction pattern looks like. So quite often people say that from the Fourier transform you actually get the diffraction pattern. Please bear in mind that I was introducing, when I was talking about the information transfer through a lens, my object creates a periodic pattern at the back focal plane, and if I use this information of the back focal plane as an object to project for the subsequent projection or intermediate lenses, I form an image like this. The magnifications and resolutions I achieve from this kind of an image is usually significantly different from what I directly see within a Fourier transform. These are some subtle differences which you will see when you practically do this on a microscope. But in reality, this kind of information at the back focal plane becomes the object for the subsequent projection lenses, and that is how I get a diffraction pattern. Now, what is interesting is we call these spots here as somewhat related to the reciprocal lattice, or this is kind of a projection of a reciprocal lattice. So, we can now relate all these through what is called as Miller's indices, and you can start indexing which particular set of planes these diffraction spots correspond to, and that process is called as indexing of a diffraction pattern. You may not necessarily have an instrument which has the resolution limit to resolve the lattice spacing within a sample, but you will always get a diffraction pattern, because if you remember, my resolution is limited by the kind of defects that my lens has. So, and also the restriction that I have when I have an aperture at the back focal plane, or based on the numerical aperture of the objective lens as well. But when my object is only from a small region here, I can still get meaningful crystallographic information from a material even if I am not able to resolve the details through an image. So, this is what makes electron diffraction a very powerful tool. So, in short, electron diffraction is a powerful technique in transmission electron microscope from which you get crystallographic information. Let us draw some parallels between electron and X-ray diffraction and understand how these are slightly different from each other. So, if I compare X-ray versus electron diffraction, in X-ray diffraction, the X-ray scattering occurs when the negatively charged electrons within the specimen are driven by the oscillating field of the incident X-ray. The response from these electrons are as a consequence of the interaction of the field of the X-ray with the field of the electron or the electron cloud within a crystalline sample, and which are again periodically arranged. You get some kind of a resonance, or let us say a constructive interference, and you get the X-ray diffraction pattern. So, it is essentially a sort of a field-field interaction when it is in terms of X-ray diffraction, and the emitted fields radiate from each of these electron sources, and the resultant is the outward scattered radiation is sort of the X-ray diffraction pattern, which you see often as a variation in intensity, and each of these peaks correspond to some positions which are in turn equivalent to the lattice planes that are satisfying my X-ray diffraction criteria. In electron diffraction, the incident electrons are scattered by electrons and the nuclei present in the material. Remember, unlike X-ray, where the propagating X-ray is just sort of photons of X-rays, you have electrons which are charged particles interacting with the specimen. So, the nature of interaction is a direct particle and electron or a nucleus kind of an interaction. So, you also have the additional Coulombic interaction apart from a field-field interaction the way you have in X-ray diffraction. So, what then happens is the scattering cross section, which is kind of a measure of probability of having a successful scattering event, is much more stronger in terms of electron diffraction, unlike in an X-ray diffraction. So, X-ray diffraction is a field-field interaction, whereas electron diffraction is a Coulombic interaction. So, as a consequence, the strong scattering leads to a pronounced, very strong electron diffraction pattern, and it is extremely sensitive to the local atomic structure. And also remember, the specimen I was mentioning to you can give you slight bends within the specimen, also can have small misorientations of the internal atomic planes, and even these small deviations can give you a variation in the diffraction patterns as well. So, quite often within a small region of a specimen, from one portion you may see a very symmetric diffraction pattern, whereas just adjacent to it you might see significantly misoriented kind of a diffraction pattern. So, what is the objective of doing all this electron and X-ray diffraction? You would want to solve an unknown crystal structure within a material. So, to understand how to solve this crystal structure, let me first define what is called as the structure problem. Within any crystalline material, you know that atoms are periodically arranged in some specific pattern, and we have the concept of the Bravais lattice, and we know that within a crystalline sample the atoms are arranged in a periodic fashion. Now, when I want to determine how these atoms are arranged, I would typically go to one of the scattering methods, one of the diffraction methods that I just told you, either X-ray, electron or neutron diffraction. But either way, we are solving the crystal structure. The crystal structure problem, if I simply put it, I have atoms arranged in some periodic fashion within a unit cell, and I would have three different parameters that determine the crystal structure. The first one is what are the dimensions of this unit cell. So, if I call these three as A, B and C being the unit cell vectors, I would want to know what my unit cell parameters are. The next thing is what are the angles here within my unit cell, and finally within this unit cell where the atoms are sitting. So, therefore, when I have an unknown crystal structure and if I am resolving it by using either X-ray or electron diffraction pattern techniques, I have a threefold structure problem. Essentially, I would like to determine the unit cell parameters. Most commonly, when I do X-ray diffraction and I do not do any Rietveld refinement, or I do not do any computation of diffraction patterns from assuming a sort of a crystal structure, or even if I am doing this with regular electron diffraction, I would typically determine just the unit cell parameters. Then you have to determine the symmetry as well. So, I can take a particular crystal system, start by assuming that the crystal system has a certain symmetry, and I can simulate the expected X-ray or electron diffraction patterns, and I can check if my assumption is actually correct and if it is matching with the result I get, and iteratively I can converge towards solving the symmetry of a crystal system as well. But if you notice the electron diffraction patterns, inherently, because I am looking at the two-dimensional distribution of intensity, what I then have is inherently some signature about the symmetry, because I am looking at the projection of the information from a crystallographic plane at the back focal plane. I inherently get information on how the two-dimensional distribution of these atomic planes is, which is reflected in the diffraction pattern as well. There are ways in which you can get this information on symmetry strongly. That is, I can choose to either illuminate my specimen with a parallel electron beam, where my interaction volume within a specimen is like a cylinder, or I can converge the electron beam and I can have sort of a illumination within a truncated cone kind of an area, and in this case I get what is called as a Kikuchi band pattern or a convergent beam electron diffraction pattern. Here I typically end up getting a spot pattern. Let us understand this in a little more detail as we go along. So, from this kind of convergent beam electron diffraction study, I can actually determine the symmetry as well. And the third thing is, where do I know where these atoms are sitting within a unit cell? In X-ray and neutron diffraction community, there is something called as Rietveld refinement, where you assume there is a certain crystal structure model, and then you start seeing by placing or displacing the atomic positions within this crystal structure how my intensity distribution varies, and I can converge towards a solution there. But when I am doing this in transmission electron microscope, because I can also see the projected images, if I have a microscope that can resolve the lattice fringes within a crystalline sample as well, I can actually see how my atomic planes are arranged, and by changing the focus within the specimen, I can obtain what is called as a through focus exit wave reconstruction, and I can get exactly where my atoms are sitting. Now, this idea is on exit wave reconstruction and through focus. You will get to know a little bit more in detail when I talk about high resolution imaging in TEM, which will come at a later stage. But for now, you please understand that within transmission electron microscope, you can determine exactly where the atomic positions are through direct imaging, either by imaging in TEM mode, where you get high resolution electron micrographs, and then you do exit wave reconstruction. So, even in exit wave reconstruction, the idea is you assume a crystal structure, you simulate how the lattice image is, and you feed this and within the model, and you iteratively converge towards a solution and see that the image you get from an exit wave reconstruction is matching with the model you've assumed. So, essentially the crystal structure that we see is completely solved when I get to know what the unit cell parameters are, what my symmetry is, and what my atomic positions are as well. So, once you've determined all these three, you would have solved the crystal structure. When I am typically synthesizing a sample and I want to know the unknown crystal structure, I should resolve it by doing this kind of a thing if I am doing it in a transmission electron microscope. You can get these three with complementary synchrotron diffraction or X-ray or neutron diffraction methodology as well, and that gives you a quantitative measure from a bulk specimen. And if I do the same thing with electron diffraction and solving my crystal structure with high resolution TEM or STEM techniques, I can also do it complementarily and I would have solved the crystal structure. I am not saying that only electron diffraction is better than X-ray diffraction or only X-ray diffraction is better than the electron diffraction. As an end user, you should know for what sort of issues I should resort to electron diffraction and what sort of issues I should resort to X-ray diffraction. As an example, if I have a single phase material and I know how my crystal structure is, I am better off getting the idea of crystal structure by simply going to an X-ray diffractometer and getting the complete crystal structure solution from standard X-ray diffraction and Rietveld refinement. If I have a two-phase material and if the distribution of the secondary phase is extremely small and I would like to see where these secondary phase morphology is, how it is and where it is distributed within the specimen, then I might want to do electron diffraction. So, you should be wise in choosing, and sometimes complementary methodologies to determine crystal structure always gives you a better solution. So, let me show this structure problem sort of schematically with what kind of information I get within the TEM. So, if I look at the cell parameters, I can get it with simple spot diffraction, which is by using a parallel beam of electron beam interacting with specimen, and I collect the projected electron diffraction patterns which typically appear like these spot patterns, and from these spot patterns I can determine from these two unit cell vectors I get corresponding lattice vectors, and then from these I know what my cell parameters are, and then within the specimen if I converge the beam I can either get what is called as a Kikuchi pattern which looks like this, or if I use a suitable convergence angle and a smaller area of illumination, and if I offset the specimen a little bit, either by changing the focus or by changing the going away from the eucentric height, there are a few ways in which you can obtain these kind of convergent beam electron diffraction patterns. From these disks, I can determine how the symmetry is. As an example, I see a specific kind of symmetry here. I think this is from a crystal of magnesium iridium bromide. I am not sure, I do not remember exactly what kind of a scenario this is, but you can see that from the spot patterns, by intentionally changing the angle of convergence and changing the focus within the specimen as well, I can in fact illuminate in such a way that I get a disk pattern, and I can actually check what kind of symmetry I have, what kind of information I get here. If there are some defects, can I highlight these defects, what kind of image or information I have within these disks as well, and it is actually a very powerful tool with which I can get excellent symmetry information from a specimen. And then once I know these two, when I determine the cell parameters and then I get the space group information as well, I can get the specific atomic parameters from a through focus exit wave reconstruction. So, from conventional high resolution TEM imaging, by changing the focus, I can get projected images from the crystalline lattice, and sequence of these high resolution TEM images by changing the focus in small steps of, say for example, 2 or 4 nanometers. I can collect a series of projected images and I can reconstruct something like this, and then I know how my atomic arrangement within the crystal is as well. And once I know all these, I can resolve a crystal structure. So, at this point, I hope I have impressed upon you what is the necessity of electron diffraction and how can you get crystal structure information within transmission electron microscope by using complementary techniques. By simple parallel broad beam illumination, I can get spot diffraction patterns. Then through convergent beam techniques, I can get symmetry information, and through high resolution techniques, I can get positional information. What we will do now is stop here, and in the next lecture, we will try to understand some basics on crystallography, arrangement of atomic planes, what is real space, reciprocal space, the concepts of stereographic projection, and how can I relate the spot patterns I get to projection of reciprocal lattice. Thank you.